And we're back. Welcome back from your weekend. Today we're going to switch gears a little bit, focus on so-called radial basis function. But before we begin, let's cover some administrative bits. Our final project on support vector machines, but in this we will look at optimization and how that impacts the performance of the support vector machine formulation. And this will be out 28th of April, which is Tuesday today. And for this, you'll be doing two parts, a presentation, and presentation slides will be due, as well as you'll be giving a presentation up to 30 minutes each, so it will be comprehensive on the 4th of May, 2020, from 6 p.m. to 8 p.m. And then the final project itself, all of the experiments, will be due on the last day of finals, which is the 8th of May, at 8 p.m., which is the time when residence halls close. So while we're not in the residence halls, we're not on campus, we're purely online, we're going to adhere to that schedule just so that everything is scheduled in among other courses to keep things orderly. Okay, where we last left off, we talked about the solution to the support vector formulation, but we included this idea of a margin violation. We talked about soft margins. And so in that, we introduced a new variable, xi, and xi was used to effectively absorb the extra amount by which the margin was violated. You can think of it as a little bit of looseness or slack, as it were. And so when we did the dual formulation and we solved that, we found that that imposed an upper bound, a limit on our Lagrange variables, our alpha n. That limit was c. And in doing so, we effectively maximized the margin, but we also minimized the total amount of margin violation. And this term here, that c, that limit on our alpha n, so Lagrange multipliers, that acts a lot like regularization, a regularization penalty. Okay, so let's switch gears. We're going to talk about the so-called radial basis function model. Now, in radial basis function model, every single data point, xn, is going to influence the hypothesis. And this influence is going to be based on the magnitude, that difference between xn, each in-sample point, and the query point of interest, x. And so it's called the radial basis function. The radial part corresponds to this magnitude, and the basis function part corresponds to this exponential. So if you think about what happens, it's almost like a Gaussian, right? If you center this basis function, this Gaussian, this exponential, at a particular xn, and as you go distance-wise in some direction away from xn, that's going to be our x, it could be over here, or it could be on the other side, well, the output is going to tail off, is going to decay. And that's where that distance comes in, that distance between xn and that x. And so you have one of these associated with every of these big N many in-sample points. And this is called the basis function. And it looks almost like an interpolation. The output of our hypothesis is some weighted combination, where the weights are Wn, weighted combination of an influence, a soft influence, the decaying influence, relative to each of the in-sample points. Now, of course, we have a parameter here, gamma, and gamma can be either very large or very small. And we'll talk about the impact of gamma in a few more slides. So let's take a look at how you might learn this radial basis function. And the idea behind this radial basis function is to mimic the ground truth class labels, the yn. So here we have our hypothesis, h of x. It's governed by a set of parameters, big N many parameters, w1 through wn. There's a single parameter w associated with each one of our in-sample points. Now, of course, if your data set is large, if n is big, you're going to have a lot of parameters, and that's never good from a VC dimension standpoint. But nonetheless, we have these parameters, and we have this expression for h of x, and it's a weighted sum of each one of these interpolations, and it's modulated by this gamma can think of it almost like a sensitivity, a capture region, right? Gamma will modulate the width of this radial basis function. Okay, so here we have our data set, and now the idea then is to drive in-sample error to 0. And we're trying to do that by choosing our weights such that our hypothesis, thusly defined h of x, on a particular input xn is equal to y of n. So we're trying to get this weighted sum to be exactly equal to y of n when we input xn. And we're trying to do that across all of the data. All right. So here, this is our criteria for minimization. And so if we evaluate h of x on xn, h of xn, it's this expression. Well, if we have this loop here, this summation, it's the weighted sum of the mth weight times the mth radial basis function, and we're trying to get that weighted sum to equal yn. Well, yn is the corresponding ground truth label, real value, associated with this xn. Okay, so here we can take this, and this gives us a set of equations. Now, certainly we can call h of x on x1, on x2, on x3, up to including x big N. And so here, if we take a look at this expression, if we have this definition for h of xn equal to yn, well, that's one equation. So we can call h on xn, h of xn, and we can do that for h of x1, h of x2, up to and including h of x big N. So now that we have these expressions, each one of these is an equation in n unknowns because we have n many of these weights. Those are all unknowns. And we have n such equations. Here are the equations, n equations. And each one of these has n unknowns. So we can take this expression and we can write it in matrix vector notation. And so here, if we look at this expression, along the rows, we have h of xn. And along the columns, we have the iteration here for that index m, looking at that mth radial basis function. So here along the columns, we have the basis function, right? The mth basis function. And along the rows, we have the equation, the evaluation of h on xn. So let's take a look at this expression. So if we take this first row and we multiply it by our w vector, where w is of rank n by 1, big N by 1, we get exactly this expression. So let's take a look at the first equation. So we have radial basis evaluated on x1. There's the first term, second basis function, the third basis function, the nth basis function, times first weight, second weight, third weight, the nth weight is equal to y1. Okay, so we get exactly this expression, and we can look at all n equations and n unknowns by looking at our basis function evaluations on each of the in-sample points. So we're going to call this linear system, our n equations and n unknowns, we're going to call that phi. So we multiply phi, coefficient matrix, evaluated using this basis function. We're going to multiply that by our w vector and set that equal to the target's yn, these real values. And so we can solve for w, assuming that our coefficient matrix, phi, is invertible. We can solve for w by just inverting phi multiplied by y. So we're going to left multiply both sides of equality by phi inverse. So we have phi times w is equal to y. So we left multiply phi inverse times phi. W is equal to phi inverse times y. Well, this goes to identity, and we're left with W is equal to phi inverse times Y. And so if our coefficient matrix phi is invertible, we get exact interpolation. We're essentially interpolating, using these weights, to interpolate each one of these Y values, these outputs corresponding to the xn that we're evaluating this radial basis function a sub x on. Okay, so this is exact interpolation. Now let's take a look at gamma, this parameter for this interpolation. If gamma is very small, what happens? Well, this decaying exponential, it decays at a slower rate, and the result is that the radial basis function is wider. If gamma is large, this decaying exponential, decays faster, and so this radial basis function is going to be more narrow. So here we have a bunch of xn's. So you might call this point x1, this point x2, this point x3. And if you're evaluating your radial basis function, well, these are the individual basis functions. You're centering on each one of these data points. So there's the first one, centered at x1. There's the second one, and there's the third one. So you add them up using a mixture of weights, and you get this blue curve, this big blue curve. And so that's what happens when gamma is small. When gamma is large, well, you're going to get this curve. We have the individual radial basis functions for each one of our data points, and with a large gamma, you notice they decay much faster, right? So you're doing more smoothing for gamma small, less smoothing if gamma is really large. And of course, the output here along this blue curve is going to be the output of h of x, okay? Your hypothesis. All right, so you can use the radial basis function. Granted, yes, it outputs a real value quantity, but you can use radial basis function to build a classifier. And just like we did with using regression as a classifier, we can actually take our class labels +1, -1, and learn the radial basis function doing exact interpolation to output values of +1 or -1. And when we learn that, of course, if it tries its best to get +1 or -1 output for the final version of the weights for this radial basis function, it'll still be positive or negative, so we just wrap that in a sign evaluation. And so here we can use the radial basis function to build a classifier using the same technique that we learned about when we discussed using regression to solve the classification problem. And so in this, you can learn linear regression for classification. You take your scores, S, and you set your score to be equal to +1, -1 labels, and you're literally minimizing the squared error loss between the score of this radial basis function and these y values, where your y values are +1 and -1. And then once you get the resulting weights for your radial basis function, then you wrap that in sign, and there's your final hypothesis. So let's take a look at some comparisons between radial basis functions and something called nearest neighbor. And so nearest neighbor is based on the idea of birds of a feather flock together. That means that data points that are similar tend to have the same label. And if you think about it in feature space, let's say you had two data points, and here's my first feature x1, this is my second feature x2 axis, and let's say I have a point here, and this point is x1 vector, so that would be x11, x12. And let's say you have another data point, x2, that's very close by, and that has features x21 and x22. Now, of course, if these points are very similar to one another, well, they're most likely going to have the same label, right? And that label, if you're talking about classification, that would be a plus label, and that would be a plus label. Whereas something that's much further away, let's call that x3 vector, that would tend to have a different label if it's not the same. Because if it's similar, that means the features are going to be very close to one another, which means they're going to be in very close proximity to one another in feature space and most likely have the same label. So this idea of birds of a feather flock together means that similar data points will tend to have the same label. So therefore, what k-nearest neighbor does, it says, okay, well, if you're trying to do classification, well, you take a point knowing its label, and all the other points that are nearby, you adopt that same label because their feature values are very close to one another. And so by adopting the y value of a nearby point, you can actually perform classification. And this k nearest neighbor distance, this near criteria, nearest, is defined using Euclidean distance within the training set. And so as k gets smaller, it's less smooth. As k gets larger, meaning the first nearest neighbor, the second nearest neighbor, up to the kth nearest neighbor, as k gets larger, it's more smooth. Now, certainly with a Gaussian, something like the radial basis function, you can make it even more smooth. So let's take a look at what I mean by this. So this frame on the left is an example of k-nearest neighbor classification where you're adopting the class label of the so-called nearest point. So here we have the blue circles, that's one class, and the red plus, that's another class, and certainly all the points around it, based on your Euclidean distance, you're going to adopt the same label. But at some point, you switch over, an abrupt change to another label. And so this has the same effect as radial basis function if you change the radial basis to be a cylinder instead of that smooth, nicely decaying exponential or Gaussian, right? If you use the cylinder, you get this behavior because the k-nearest neighbor, you have these hard boundaries, so that's the same as saying you're the same label, same label, same label, and then you drop off to nothing. And so these so-called similarity-based methods take the label for one data point and based on measurements from the features, propagates labels to other data points. And you can do classification like this, and k-nearest neighbor is one example. Okay, so let's take a look at this issue that we have with this k-nearest neighbor as it pertains to the number of parameters. And so we said with a radial basis function, we have big N many parameters, W1, W2, W3, up to and including Wn. Now, of course, N is the size of the set of in-sample points based on your data. Now, of course, if N is very large, you're going to have a large set of parameters to solve for, and that's never good from the VC dimension standpoint. And so what we can do instead of using a single weight or parameter for every single data point, we're going to define a set of centers, and we're going to use these centers, k many of them. And the assumption is that k is going to be much, much smaller than the number of data points. So let's define these centers, and these centers, mu1 is the first center up to and including mu sub k, which is the kth center. So there are k many centers. And these centers just happen to be defined in the same d-dimensional feature space as our data points, right, in the same input representation. And so now we're going to use as the place we center the radial basis function, we're going to use these centers instead of these data points. And in doing so, we're significantly decreasing the number of parameters in our radial basis function. So if we do this now, we're using the centers or aspects of the centers to drive or govern what this radial basis function's output will be. And so when we take our weighted sum, we're going to take our weighted sum relative to this radial basis function, but instead of radial basis function being defined for every in-sample point, it's being defined from the perspective of every center. So now, with this change, we can decrease the complexity so it's not brittle or so dependent on the size of the set of in-sample points. And our hypothesis h of x becomes the weighted sum for k goes from 1 to big K, the number of centers, wk, a single weight for each one of these centers, times the radial basis function for our input parameter x relative to these k many centers. And so we do that relative to the center, and now our complexity is greatly reduced because k, by definition, as we had stated at the outset, is much, much less than the number of data points. So now this problem becomes how to choose the centers, our mu sub k's, and how to choose the weights. So because we had too many parameters with these w's, we pick a number of centers and we let them, these centers, have influence on the neighboring points around them, rather than using every single in-sample point, which doesn't work. If n gets bigger, our complexity blows up. Okay. So the idea then is to minimize the distance between each one of our in-sample points xn and the center mu k that's closest to it. And so this is what k-means clustering is, and this is an unsupervised learning algorithm. We're not looking at the ground truth label, the y-ends. We're only looking at the features associated with the x-ends. So what do we do here? We split our data into clusters, so we just assign them into clusters. And the first cluster is sk. That's a set of data points. S1 is a set of data points, and the kth cluster, sk, is another set of data points. So we have big K many groups of data points, and these groups are our clusters. And so we split our data, our n many in-sample points, into clusters, k many, S1 through sk, and now we're minimizing the following objective. For every point within a cluster, we minimize this distance between the point and the cluster, and we do that over all of the big K many clusters. That's what the outer sum means. So we're trying to balance this, and what we're trying to balance is effectively make the clusters as compact as possible. So here we have mu1, here we have mu2, here we have, for example, mu3 in feature space. And let's say we have a bunch of data points. Here are my data points. Here are some data points. And here are some data points. You're effectively, what this objective says is to assign the points to clusters. This is S1, S3, this is S2, and this is S1. Assign the points to clusters such that you minimize the within cluster distance across all of the clusters in your data. And so this is a problem. This is, as stated, it's an NP-hard problem because you have an exponential number of assignments of points to clusters. And if you think about it, for the first point, you have k many choices. For the second point, you have k many choices. Up to including the end point, you have k many choices. So this is equal to k number of clusters to the n power. That's absolutely huge number of assignments that you could make in trying to solve this minimization problem. Now, of course, you can approximate it is the best thing you can do because it's an NP-hard problem. It's exponential in the number of cluster assignments. So you never solve this directly. And so there's an approach, an iterative algorithm called Loyd's algorithm that we can use to solve this, and it'll converge on a local minimum, but it's feasible. Okay. And so what we do with Loyd's algorithm is we fix one quantity, the cluster assignment, and then we update the cluster center values, and then we fix up the assignments holding the cluster values fixed. So we will stop here and pick back up next time with Loyd's algorithm and finish our module on radial basis function. So with that, I will see you all on Thursday.